All right, so it's about time to get started with our Cumulus lecture. We're running a little behind schedule, so I may not be able to take quite as many questions on this one, but we're going to try and get through it and give you guys a solid understanding of the parachain side of Polkadot. So Cumulus is the glue which attaches substrate-based chains to Polkadot, converting them into parachains. For our outline, we're going to cover what is Cumulus. We're going to cover Cumulus and para-relay communication, how Cumulus keeps a parachain node informed, how Cumulus enables parachain coallators to generate collations, otherwise known as parachain blocks, and to advertise them. Then we're going to show how collations, or parachain blocks, as well in the format that they're delivered to Polkadot validators, how those enable parablock validation. And finally, we're going to cover how Cumulus enables runtime upgrades. All right, so firstly, what is Cumulus? It is a collection of code libraries extending a substrate frame chain so that it can interface with the Polkadot API, run relay chain-based consensus, and submit parachain blocks for validation. So in order to understand Cumulus, it's useful to understand how the various components of Polkadot SDK relate to each other. Firstly, we have Substrate, which is a blockchain building framework. But it only enables you to build solo chains on its own. It's split between runtime and node-side code, as you would know. Both Polkadot and Cumulus extend Substrate. So Substrate was used to build Polkadot. Substrate also provides generic types and interfaces to Cumulus, and the Polkadot relay chain it provides these APIs, it exposes these APIs to Cumulus-based parachains. All right, so some review of terms. What is a collator? It is a part of the consensus authority set for a parachain. It authors and submits collations to relay chain validators. And collations are information necessary for validators to process and validate a parachain block, resulting in that block eventually arriving on the Polkadot relay chain. Now, collations include a number of things: upward and horizontal messages, new validation code, the resulting head data from executing a parachain block, a proof of validity, process downward messages and horizontal messages. So those are the contents of a collation, but then this proof of validity, what is that? It is the information necessary to mimic parachain state and transactions for the purpose of executing a single parachain block. And we will revisit that in more detail. All right, so for our Cumulus key processes, firstly, we follow the relay new best head and update our para new best head. Now, the new best head is a block at the head of a fork that is most preferred by Babe. So that includes a couple conditions. For instance, for a block to be preferred by Babe, it would need to descend from the finalized block, so it can't be outside of possible descendants. Also, it is subject to a slightly more complicated form of longest chain selection. So rather than purely the longest chain, this would be the chain that has the most primary block authors, where primary block authors have a specific meaning within Babe and Grandpa. All right, so another one of our key processes is to follow the relay chain finalized block and to use that to update our parachain finalized block. Thirdly, we need to request parachain blocks that were not shared by peers from the relay chain. That is data recovery and is actually based on the data availability layer that Polkadot provides that we described in this prior talk of mine. So the final process is collation generation and announcement, also known as parachains building blocks and communicating those blocks both to other parachain nodes and to the validator set. So I can take a few questions this time, but not very many. So this is one.
Just to see where we're at, like, at what stage is Cumulus required? Is it like when you start a new parachain, so you kind of like sync up with the relay chain, or?
Cumulus is a constant, ongoing process. These processes that I'm describing here, the, say, keeping up with the progress of the relay chain and updating things, these are going on before you author every single parachain block. So this is an ongoing piece of communication that's necessary in order for a parachain to follow the relay chain and then add to its parachain.
Okay.
All right, and we'll describe how that communication takes place. So in our diagram here, we have Polkadot validators on top. We have a collator node on the bottom left, parachain full node on the bottom right. You'll notice that both the collator node and the parachain full node have this thing called a tethered relay node. Now, parachain full nodes actually have Polkadot relay chain nodes attached to them. Reason being, parachains need to keep track of what's going on the relay chain. Parachain finality piggybacks off of relay chain finality. The parachain notion of inclusion piggybacks off of the relay chain notion of inclusion and say best blocks to build on and whatnot. So as participants in a parachain, you need to keep track of what's going on the relay chain. The most convenient way to do that is to just run a relay chain node. And so that's what the parachains do. And collator nodes, so describing our white arrows here, these are collations being made. So these are bundles of information for validating parachain blocks. So essentially it's like the parachain block itself being communicated. The collator is sending these parachain blocks up to their tethered relay nodes to a subsystem in the relay node called the collation generation subsystem, which sort of pairs with a parachain node and communicates with it. That collation generation subsystem will then sort of repackage and redistribute our collation to Polkadot validators. So that's kind of how our piping works, how information's getting passed around. And finally, the collator node will advertise blocks that it has freshly made. It will advertise them to other parachain full nodes and other collators. So that's our sideways arrow at the bottom, pointing from one green box to the other. Sure.
So the parachain full node, it only has the blocks for one parachain. It's not...
Yes, just for one parachain. So this is a single parachain, and this is a representation of one collator node on that parachain and how it would communicate with other full nodes, including other collators.
But the full node itself is a collator as well, right?
So not all parachain full nodes need to be collators. They can be just nodes. In the same way that Polkadot has nodes and validators, parachains can have nodes and collators.
Okay.
And essentially the difference in responsibilities is just that collators are responsible for occasionally authoring blocks, whereas parachain full nodes would never need to author blocks.
It will be importing the blocks from the relay chain later?
So the happy path for a parachain full node to get access to blocks would be that collators from their same parachain pass them that block information via gossip. Now the unhappy path is, oh, we haven't been gossiped a candidate, even though we can see from our tethered relay node, we can see that there's a new candidate receipt that has shown up on the relay chain for a new parachain block. We can see that our parachain is progressing, but we haven't received any of the blocks from our parachain recently. That's where Polkadot data availability steps in, and where we can use the proof of validity that we've stored to kind of restore that information to a parachain full node when it's in the dark. And the arrows that I'm adding to our diagram here do just that. Our red arrows represent data that's flowing down from the relay chain and from the validator set flowing down to parachain nodes. These are new best heads, these are finalized blocks, and these are also requested parachain blocks. All right, so how do we handle incoming relay information? We're going to cover this. Before addressing collation generation, let's first address the other three key Cumulus processes. These drive parachain consensus, and they ensure the availability of parachain blocks. Together, they keep parachain nodes up to date such that collating is possible. All right, so parachain consensus. Parachain consensus is modified such that it achieves sequencing consensus but leaves finality to the relay chain. But what is sequencing consensus? You decide on an accepted ordering of blocks and of transactions within a block. Sequencing consensus requires that we update our knowledge of the new best head of the parachain. That way, nodes are in agreement about which block to build on top of. Cumulus sequencing consensus is modular and changeable. There are many options for how you could choose to sequence your blocks. One option is, and the option that I think by default all parachains are using right now is called ARA. That's just a simple round robin. When it's your turn as a collator, you can produce a block. And if you choose not to, then it's no longer your turn next time. Someone else gets that opportunity. And so you just rotate through the entire collator set, each collator getting their turn. That's ARA. Now, there could be other styles of consensus used. For instance, Tendermint style, where you would get a quorum of collators that would all, say, upvote a single proposed parachain block. So maybe an ordering of transactions within a block, and then all of those collators say, yes, this is the one we want. Then any of those collators could then submit that block to the relay chain. We have not seen any parachain implement Tendermint style consensus, but there's no reason why it could not be implemented. And again, these things are very plug and play. We have made consensus totally modular. All right, so block authoring is import driven. Let's describe what that means. So collators are responsible for authoring new blocks, and they do so when importing relay blocks. So honest collators will choose to author blocks that are descending from the new best head, which is frequently a new parachain candidate that was included in the latest relay block we've seen. Now, how does this look in code? So a very, very simplified version is this loop here. In our loop, we import a relay chain block from a stream. Then with our imported block, we would, let's see. So if our imported block is awaiting a parachain candidate, so essentially if the relay chain is awaiting a candidate for our parachain associated with the execution core assigned to our parachain, then it's time for us to author a block. So we have our parachain trigger block authoring, and that produces ideally some proof of validity. And we're going to take that proof of validity and we're going to distribute it in the form of a collation to relay chain validators using the distribution diagram that I showed you guys before. All right, so similarly for finality, we need to update parachain finality based on relay chain finality, and that also can be simplified in the form of a loop. So we have a stream of freshly finalized relay chain blocks, and we just, when we have a new one, then we put it in a variable. We figure out whether our parachain might not have a candidate included in that relay block. So it's freshly finalized, but there might not be a freshly finalized block for our parachain. So we check, do we have a new parachain block in this freshly finalized relay chain block? If there is one, then great. We pull out some new best finalized parachain block, and we set our finalized parachain block to that one that we pulled out of the relay block.
So does only the backers send to the parachain the finalized blocks in this case?
So the way that coallators have access, well, coallators and parachain full nodes, the way they have access to finalized relay blocks is actually through the relay chain itself. See, the coallators, they are running Polkadot full nodes that are attached. And so the Polkadot full node is taking part in gossip. They're receiving relay blocks, and they become aware when there's a new finalized relay block through that normal gossip on the relay chain. But this node has a special subsystem turned on called correlation generation. So when it sees a new relay chain block, it does certain things that other Polkadot full nodes don't do. It triggers to try and communicate with the collator node and to tell it to, say, generate a new block or update its finalized block.
So the choice to have, so all parachain collators are full Polkadot nodes?
Yes.
And isn't this a bit like heavy or like more?
So in theory, yes, you could make it lighter weight by. Now I think this might be an ongoing progression of trying to migrate those relay nodes away, such that we could have, say, relay nodes that can choose to service coallators that are not directly attached and running on the same machine. Like we could do that in theory. I think there's even code for it in the code base. I'm not sure if that's being actively used at the moment. But yeah, in theory, it would be nicer to run these things separately, but it was awfully convenient to get this thing off the ground to run them on the same machine. And I think the amount of work that just a relay full node is doing is pretty small compared to the amount of work that a collator node on a parachain is doing. So I think proportionally it's still fine. Yeah, let's see, where was I? Oh, yeah. So ensuring availability, this goes back to our Polkadot data availability talk. So as a part of the parachains protocol, Polkadot makes parachain blocks available for several hours after they're backed. Why is this needed? We covered that it's needed for approvals, so that all approvers are getting copies of the proof of validity, and it's also needed in the case of a malicious collator, so that other participants, other parachain nodes, and other collators can get the bodies of parachain blocks. So a brief aside about the candidate receipt. The proof of validity is too big to be included on-chain when a parablock is backed, so validators instead produce a constant-sized candidate block receipt to represent the freshly validated block and its outputs. The candidate receipt contains many hashes, so its main use is it contains mainly hashes, so its main use is to verify the correctness of known proofs of validity. And the candidate receipt only references a proof of validity, it cannot substitute it. All right, so we covered this malicious collator example a little bit in our prior talk, but nailing some of these things down with multiple visualizations is not bad. So we have this malicious collator, and it is sending a proof of validity up to the relay chain. This is first being sent to backers. If they back it, then it goes to data availability, maybe gets included on the relay chain or even finalized. All of this can happen without the malicious collator telling any of the other collators or even any other parachain full nodes about the existence of this new block and its associated proof of validity. This can cause problems because then other collators are not up to date with the head of the chain. They can't make new collations. So how are we handling this? Firstly, these collators, they see, as I was describing earlier, they see this candidate receipt on the relay chain. They can see it because they have a Polkadot full node attached to them that it's gathering blocks for the relay chain. So they can see that their parachain has a new block, but they haven't received the block body. So again, this is not good. You can't make new parachain blocks if you're not up to date. So we get the Polkadot validators involved with our data availability layer, providing this proof of validity to the collators so that they can re-execute these changes and update their state. All right, so we've handled all of the parts of Cumulus that keep collators up to date. This is information moving down from the validator set or down from the Polkadot relay chain to collators and other parachain nodes. And now we get the payoff. Our collators are up to date with the newest head of the chain. They can finally contribute. They can create collations or parachain blocks, and they can advertise them. All right, so first the generation. This is the last of our key processes that parachain collators are involved in. Firstly, a relay node imports the block in which that parachain's availability core was vacated. Secondly, the collation generation subsystem within that relay node, it requests a collation from our collator. Then parachain consensus decides whether it's this collator's turn to author. So if we're doing ARA consensus, then it's in our round robin taking your turn scheme, is it my turn? If it's not my turn and I'm a collator, I just wait because it's not my turn. For Tendermint, it might be something like, oh, can I try to build the block that we've all decided someone should build? That might be our scheme there. So then a collator proposes, seals, and imports the new block. And finally, the collator bundles that new block and information necessary to process and validate it, a collation.
Imports means communicating it to the...
Yeah. So imports actually means something a little different. That's imports onto its own chain and essentially executes the block. So this is a collator imports the block into the parachain, and the block ends up executed through the parachain runtime, and then the parachain state is updated accordingly.
But it's not finalized at this state.
No. So this is one fork of unfinalized state that the parachain has progressed. All right, so revisiting yes, it's time to revisit distribution. So there was a little bit of detail involved here that I didn't go into before as to in what order do these white arrows that represent distribution execute. So first, we have our collation, which is sent to our tethered relay node. That is our upward arrow from the collator node to our tethered relay node in purple. So we send our collation up to that relay node. It gets repackaged and forwarded to our backing group, so a subset of Polkadot validators. Then at least one of those backers needs to respond, signaling its approval, that it has validated this block and deems it valid. What happens then, and only then, is that the collator node starts to gossip that block candidate to other collators and other parachain nodes. Now the reason behind this, the reason why we send a block up to validators first and get their okay before sending it over to other nodes essentially has to do with proving that we're not spamming other parachain nodes, to prove that we're not engaging in a DOS attack. by getting a little bit of buy-in from the validator set, we are showing that this block means business and that we're not just throwing illegitimate candidates at everyone and overwhelming their systems.
Excuse me, in the previous slide, the Polkadot validators, this is the backer.
Yes. So backers are a subset of Polkadot validators, and you could swap in the term backers for Polkadot validators there. All right, so how does this distribution look in code? So we prepare the announcement of a new parablock to peers using this function announce with barrier. And then we have this result sender that comes out. We want to send this result sender to a validator, to a backer, and eventually, if a backer likes the candidate that we've produced, that backer is going to use our result sender to send a result back. And that's the green light that we're waiting for in order to start gossiping.
So, a question. We have multiple parachain full nodes. We have multiple collator nodes, okay?
Yeah.
Each of them can have different blocks produced and then sends them to the backers. So the backers will have maybe at worst case, n collators blocks, right?
This depends on which style of consensus you're running. So in the case of, say, free-for-all consensus, which is kind of what you're describing, there is a type of consensus called free-for-all, where collators essentially just build whatever blocks they want, whatever valid blocks they want, that is, and send them up to backers. In practice, Polkadot chains tend to run more restrictive forms of consensus, like ARA, for instance. And in that case, you have only one block author for a particular slot, or maybe a couple. Maybe you have 2 or 3 that are picked each time, and maybe you have 2 or 3 collations that are competing for the backer's attention, but it won't be like the entire collator set that's spamming these things.
Yes, thank you.
All right, so we're gonna take a look at how Cumulus collations enable parablock validation now. What is runtime validation? It is when the relay chain ensures that every parachain block follows the rules defined by that parachain's current code. So we saw this diagram earlier. We are taking previous state and transactions and a state transition function. We are applying those transactions to the previous state, following the rules of our function, and we get out some new state.
Can
now
you just
the relay chain.
slow down a little bit? I'm like.
All right.
Yeah, thank you.
Yeah, so validators are trying to ensure that this state transition has been executed faithfully by collators and by other validators, but we have a problem. So on the relay chain, we need to be able to execute runtime validation of a parachain block without access to the entirety of that parachain state. The parachain state is really big, and we can't just send it around everywhere, so it's not available on the relay chain. So how do we get around this issue? It's made possible using a couple building blocks. These are the parachain validation function and the proof of validity, which are delivered within collations. And we're shortly going to get into just what the proof of validity contains and how it enables this validation. All right, so the parachain validation function, or PVF. So the current state transition function of each parachain is stored on the relay chain and wrapped as a parachain validation function. This shows up as like an opaque blob of code on the relay chain because we have no insight into just what type that might be. That doesn't matter because both the parachain code and the parachain state are passed to the relay chain opaquely, but they only need to act on each other. The relay chain never needs to act on either of those, so it's fine for them to be opaque. New state transitions that occur on a parachain must be validated against this parachain validation function. Why do we call it a parachain validation function and not just the state transition function of the parachain? So there's actually a little bit extra that's going on here. So the PVF is not just a copy-paste of the parachain runtime. It contains an extra function called validate block, and we'll get into what exactly that does. But in our diagram on the right here, you can see that not only is, so a Cumulus-based chain on the bottom left is sending collations to Polkadot, receiving relay chain information back from Polkadot, but also, as shown by our dotted arrow here, its runtime, its state transition function, is actually stored on Polkadot within the parachain validation function. It's that runtime, and then this function, validate block, that we'll get into exactly what it does. A little bit on what it does. Validate block is needed to interpret all of the extra information in a proof of validity that is required for validation. This extra information is unique to each parachain and opaque to the relay chain. But why? All right, so first we're going to visualize the path of parachain block validation. We take in a collation and we get back a candidate receipt, but what is happening in the middle? So we call this function called validate block. Well, first, the collation is passed into the client. The client unpacks this a bit and pulls out the proof of validity from within our collation. This proof of validity is passed to the function validate block, which converts the POV into necessary inputs on top of which a parachain state transition function can be run. The output created is called a candidate receipt.
Sorry, I didn't get this. Like, what happens? So the collation sends to the client the POV and the block, right?
So yeah, the collation, basically there are a bunch of things bundled into the collation. We'll get into exactly what those are in a second. But the important thing for kicking off this whole process is that the client pulls the POV out of a collation and then passes the POV as an input to this function validate block. And validate block prepares the POV so that its information can be used for running the parachain's state transition function. And we'll get into a little more detail on that.
And at this step, we don't run the PVF yet.
So the parachain runtime is actually, well, I guess, so when we enter this there's a box there labeled PVFs. Mm-hmm. You know, it has several PVFs within it, but the one that we're zooming in on is the PVF for our particular parachain that contains this function validate block and also contains our parachain runtime. So we do execute the PVF from the relay chain validator's client.
And this is the WASM for the parachain, right?
Yes, the parachain runtime is the WASM for the parachain.
Thank you.
All right, but what does validate block actually do? The parachain runtime expects to run in conjunction with a parachain client. Like from the perspective of the parachain runtime, you expect that there is a client there that you can interact with. But validation is occurring on a relay chain node, not on a parachain node, so there is no parachain client. We need to implement the API of the parachain client such that these host functions are available to the parachain runtime, even when it's executed within a relay chain client. The host functions, most importantly, allow the runtime to query its state, so we need a lightweight replacement for the parachain state that is sufficient for the execution of this single block. Validate block prepares said state and host functions, then runs the parachain's state transition function on top of them.
excuse me. So in previous lecture, I don't remember who gave it, but that the host functions, it's hard to have a host function, a specific, a newly created host functions on a parachain that is not on the relay chain, right? Or am I missing something?
So I'm not quite understanding.
Okay,
that
these host functions are default host functions. They are not something that the parachain developers can add to.
Parachain host functions, to my knowledge, can be unique as to whether a parachain host function will be supported for the purposes of validation. That's another question. So if you have a parachain host function that, say, is related to doing a bunch of off-chain work, maybe that off-chain work is not actually checked as a part of parachain validation. So I guess what you might be speaking to is there are a set of supported host functions like accessing a parachain state that are similar to the functions available on the relay chain, and those are the things we can actually check against in parachain block validation. All right, so in code, what does this look like? We have our function, validate block. It takes a set of input parameters and it outputs a candidate receipt. That's what the output would be in this case. So first we're going to initialize our state. So in our input, we have this storage proof, and we are going to turn it into this, this sort of temporary sparse parachain state. This state is exactly the level of detail. It has exactly the entries that we would need to execute this single parachain block. Then, based on the state that we've created, we replaced our host functions so that they target this new temporary parachain state. And finally, with this state, we are going to execute a block on top of it. We're going to take the block from our input and execute this block on top of the new temporary state that we've created. But we don't know where this storage proof comes from yet. It's a part of our inputs, but where does it come from and what is it? But first, an aside, so what exactly is going on with this host function replacement? On the right, we have our collator node, and we have the parachain runtime, which is calling host functions to access the parachain client. But on the left here, we have our validator node. And when we're executing a PVF, we again have the parachain runtime, and it's executing and trying to access instead the relay chain client. This is obviously not going to work. The parachain state is not available for us to use in the relay chain client. So instead, we remake those host functions so that rather than, well, within validate block, we remake those host functions such that they target the contents of a collation instead, particularly so that they target a kind of sparse state that we have constructed from our proof of validity, and we'll get into how that is done. All right, so to revisit our collations, so we have a bunch of contents here, and I'll describe them for you. It's upward messages and horizontal messages. These are things that we would pass up to the relay chain, and then horizontal messages would be passed back down to potentially other parachains. And we have new validation code. This is code that in a few blocks, if it's approved through a pre-checking process, this would become the new code of your parachain. And it's wrapped in an option because you're not always updating your code. You only need to do it every once in a while, and in fact, you're only allowed to do it every once in a while because Polkadot needs to hang on to that new code, and that's heavy data to store on chain. So you're not allowed to do it all the time. Then we have head data. This is the head data produced by executing this parachain block. We have processed downward messages and this HRMP watermark, which is again like just a marker of how many horizontal messages we've processed. All of these things are checked against validation outputs. So after we've run our parachain block validation, one thing that we do is we check that these commitments within a collation actually match the outputs of our validation. If we don't have the same upward messages that we expected, then even if, say, some hashes match up or something like that, we would still record that as a validation failure, because these important things that we're committed to by a block, we're not actually matching the commitment. Now, separately, we have the proof of validity contained within a collation. So this forms a validation input. You input the POV, and then you check all of the outputs of validation against all this other stuff. All right, so back on the proof of validity. It acts as a replacement for the parachain's pre-state for the purpose of validating a single block. But how can we map this POV into parachain state? It allows the reconstruction of a sparse in-memory Merkle trie. And the state root can then be compared to that of the parent header, that is the header of the parent block relative to the block we're building, and that way we know that this trie that has been constructed is actually composed of elements accurate to the parachain state as of our parent block. All right, so I'm going to show you an example of witness data and how we would construct it. Witness data is our this is our trie, our state trie that we are composing out of our POV. So our POV has information contained within the orange and green circles in this diagram. I'll describe what that information is. But essentially from our POV, we can reconstruct the whole, a whole state trie, and we can get the root of that in order to compare it to a previous block header's state root. So our orange circles here are data values that are being modified in our current block. So the block we are executing, it's modifying data values A, B, and C. Maybe we have transactions between these three accounts, and so the funds in these accounts are being modified. We need the actual data values there to change, and we actually then can hash them and build our tree out of them. Our green circles here are the hashes of sibling nodes that are required for our proof of validity. So we don't actually need the data contained within them, we just need the hashes. Then we can hash the green and orange nodes together to get our white circles. These are hashes that are constructed. And finally, we can get our blue circle, which is the head of our trie, and it's the hash present in the previous block's header. And so if that blue hash matches our the root, the state root in the previous block's header, then we know that our POV is at least valid on that basis. Finally, we have these red circles, which are nodes in the state trie that we don't need any information at all about. So this condenses the amount of information that we have to send around from collators to validators, that we have to store in data availability, getting rid of these red nodes, which in an actual state trie, there would be a lot more of those than are being shown here. Getting rid of those from our condensed representation is a big deal. Yeah, so this only includes the data that was modified in this block, along with the hashes of data from the rest of the trie. And this POV makes up the majority of the data in a collation, up to a maximum size of 5 megabytes. Okay, so in summary, we can come back, look at validate block, and we actually know where our storage proof is coming from. So when we convert our storage proof into a state trie, that is our POV being converted into this sparse state that we can then access with our host functions. And then we replace our host functions so that they access that new trie that we built, and we're off to the races. We can execute a block in essentially a foreign environment, foreign to the parachain in which it was initially executed. All right, so briefly I'll cover how Cumulus enables parachain runtime upgrades. Every substrate blockchain supports runtime upgrades, but for parachains, runtime upgrades are tougher. For instance, what happens if parachain validation functions compilation takes too long? Various bad things can happen, but essentially a malicious parachain could submit, or even a non-malicious parachain, but they could submit a parachain validation function containing their state transition function that contains code that just cannot be compiled in an efficient manner. So if it takes too long, we could, approvers might not be able to compile that code, which could result in approval no-shows, and disputes for either side might never reach a supermajority because you might have the majority of the disputers. The majority of these validators are, again, unable to validate a block because they can't compile the parachain validation function. So updating a parachain runtime is not at all as easy as upgrading a standalone blockchain runtime. We have a solution. The relay chain needs a fairly hard guarantee that parachain validation functions can be compiled within a reasonable amount of time. In order to make this the case, coallators execute a runtime upgrade first, but it's not applied. So coallators have this upgrade on deck. They send the new runtime code to the relay chain in a collation. The relay chain then executes a parachain validation function pre-checking process. And when that process is done, then the first parachain block to be included after the end of the process applies the new runtime. And Cumulus follows the relay chain using its, like these tethered relay nodes that are attached to coallators and parachain nodes. It keeps track of the relay chain and waits for this go-ahead signal to apply a runtime change. All right, so this pre-checking process has a few steps. The relay chain keeps track of all the new parachain validation functions that need to be checked. Then each validator checks if the compilation of a PVF is valid and does not require too much time, then it votes. It's a binary vote to accept or reject the proposed PVF, and a supermajority concludes the vote. The new PVF, in the event of a positive vote or a positive conclusion, replaces the prior one in the relay chain state. So the relay chain notion of which PVF we're using changes, and with the part I didn't include is with the very next parachain block, the parachain gets that go-ahead signal, and then the state transition function of the parachain is swapped out for the new one, that function which they had on deck. All right, so with that, I'll go to my references. Big thanks to Gabriele Miotti, who was a huge help putting together these slides. Also, there's a nice Cumulus overview, albeit a bit dated, accessible through my second link here. All right, I think maybe we're over time, but no, we have some time for questions. 5 minutes.
Okay. Is it right time to ask the 6 second and 12 second of the block time, then why it is twice in
yeah. So I suppose maybe we covered appropriately, but I forget. So a parachain block is backed in one relay chain block and included in the next. So both of these are check-ins that need to take place on the relay chain, and they have to happen one after the other in sequential blocks. So when it's backed on chain, that is, the backers have executed this parachain block. They've validated it and found it to be good, presumably. Then they pass these backing statements around saying, hey, this cohort of backers, we have backed this block. A block producer would then put that backing statement along with a candidate receipt for a parachain block on chain. That's what's called being backed on chain, and that needs to take place in one relay chain block, and then it's in the next relay chain block after the data availability process that a parachain block can be marked as included on the relay chain. And then separately, I guess the final step is after approvals, then a parachain block could be made final when its relay block is made final on the relay chain. But as for the 6-second, 12-second thing, it's relay blocks are happening every 6 seconds. You need to back a parachain block in one of those relay chain blocks, and then you need to include it in the very next one.
Okay, got it. Thank you.
Welcome. All right. We have another question back there. Oh, I guess no nice cubes. We have to pass mics manually.
Yeah. So my question is on the. Yeah, I'm Risha. So my question is on the whole flow of just iteration on that. So one thing is, while validating, first of all, in POV we have the header, with the resulting header, and the data to prove, and also we are submitting also array of transactions so that the validator node can compute against the runtime and kind of match the presented header if it's correct with all the state hash and the transaction and everything. So one thing is the relay chain block only stores parachain headers, only that, right? And not transactions. They've been discarded after validation.
Yeah, this is actually something Maciej and I were discussing before I came up here to present. Is we found that the transactions themselves are actually stored in the POV. They're made available via Polkadot data availability. So the POV does not only contain our information necessary to construct this state trie, it also contains our transactions needed to interface with that state trie. So and then those transactions, you're right that they don't show up on chain, because if they did, that would be too much data.
Yeah.
So we had to pack them in with the proof of validity instead.
Also, after validating, you discard them, or like, okay, it's more about data availability. After being available for validation, are they being deleted or still?
Yeah. So the parachain transactions, in a sense, they live on in the parachain state. So parachains that are keeping track of all of these transactions going way back, they still have those transactions to look back at, but on the relay chain side, those are deleted after 24 hours. We get rid of them. We don't want that data sticking around forever.
Yeah.
So then I'm guessing to be able to look at the relay chain transactions, there's like indexers that also go ahead and index the relay chain? Is that how it's approached?
Let's see if...
Just like a regular L1 or L2 where,
Yeah, we would have indexers looking at relay chain transactions, like transactions in dot on the relay chain. Yeah.
Because I think these would matter for things like Asset Hub, right? And any native asset, I guess.
I'm not so sure about that one.
Okay.
I guess that's more the realm of the Common Good Parachains team folks.
Yeah.
That's another team at Parity that handles more of those parachain, well, yeah, those system parachains, as they're now called, living on top of the Polkadot relay chain.
I'll look into it. Thank you.
Welcome. All right. Well, our 5 minutes are probably about up, and so are the questions. So thank you all.